So today is the electric field measurements lab, and then we're gonna design. You are gonna design by yourself your own electric field antenna to measure electric field transients. Okay. So one point to highlight here: the design we're gonna do today is to measure the electric field change. So if we have like a stationary electric field, it's gonna be kind of hard to measure. So it's not for electrostatics, it's for electrodynamics. So the electric field must change over time. Okay? So, and why I put in the parentheses lightning? Because lightning is a pulsive current that produces electromagnetic waves. And those electromagnetic waves, they change the electric field over time. Okay? So let's imagine that we have a cloud, thundercloud here, and a lightning happened, and then it's going to propagate the electric field in all directions. And at some point you have a metallic probe. It can be a disc, like the ones you have in front of you, or it can be a wipe antenna, can be just a single wire. Okay? So when the propagation of the electric field approaches your metallic probe, you're going to induce some charge in your antenna, in your plate, okay? And the induced charge here is related to one of Maxwell equations. What Maxwell equations is related to the charge enclosed in a specific surface? Do you remember that? Yes, Gauss's law. Okay, so according to Gauss's law, the charge distribution in that surface is going to be proportional to epsilon naught times the electric field. Okay, so that's like the first step to designing your electric field antenna. Okay, so we have certain amount of charge that was induced in your antenna, and then if we divide it by the area of your antenna, you have sigma, and that sigma is equal to epsilon naught times E. Okay? Good. Well, if we solve this for Q, we have that Q is equal to the epsilon naught E times A. Okay? But again, our electric field is changing over time. So we do have a dEdt. And if my electric field is changing over time, my charge is also changing over time. Okay? So our goal here is to measure the electric field, not measure the derivative of the electric field. And we learned probably 2 classes ago how to design an integrator, right? What is the component that do the integration? It is on the board. Come on. Yeah, the capacitor. So what is the idea here? We must plug a capacitor in the output of our antenna. So we place a capacitor, let's say here, and the output voltage of my capacitor is going to be proportional to the electric field. Why? Because the voltage across my capacitor is 1 over C, and the integral of the current that's flowing that capacitor. Okay? And look, what is the current? What is the definition of current? Charge over time. So if I have a certain amount of charge change over time or moving over time, I have current. And look here, I have the derivative of the charge over time, which is current. So if I plug this guy inside my integral, I can cancel both derivative equations, and I will have output voltage that's going to be proportional to the electric field. Okay, so what I did here I said that the voltage across my capacitor is equal to the output voltage, which is also equal to Q over C, okay? But my Q is epsilon naught, the electric field, times the cross-section area of my antenna, okay? So, at the end, we arrive at this equation here, at which the output voltage is going to be proportional to epsilon naught, the area of my antenna, the electric field, divided by the capacitance of my integrating capacitor. Okay? What we can highlight from that equation here? Someone can tell me what is interesting about that equation? What type of signal amplitude related to that equation we can get, how we control, I would say, the gain of our system. What happens if I increase the area of my antenna? The voltage increase. So if I have a big antenna, I'll have a bigger signal at the output of my capacitor. Okay? And look at that. The integrating capacitor is inversely proportional to the output voltage. So if you have a bigger capacitor, you have a small voltage. If you have a small capacitance, you're going to have a bigger voltage. Okay? Good. So that is the signal we are going to measure in the oscilloscope. Okay? If you want to convert that signal into volts per meter as a calibrated measurement, you solve for E, okay? So you have the electric field is going to be equal to the voltage you read in your oscilloscope, and then those terms here, C over epsilon naught A, we're going to call the calibration factor, because C is a constant, epsilon naught is a constant, and the area of your antenna is a constant. So those numbers, we're going to combine those numbers to get K, and K is going to be your calibration factor. So every time you multiply the voltage, the output voltage of your oscilloscope times this calibration factor, you're going to have the electric field in volts per meter, okay? Or kilovolts per meter, whatever. We're going to do this at the end of the class today. So when we measure the voltage across my capacitor, all measurement system has an input impedance. Okay? So we have to imagine that we have a resistance in parallel here. Okay? So we must deliver that current here to my integrating circuit. Okay? So the current from the flat plate antenna must go all the way to those guys, and then we measure the output voltage. Okay? The combination of that impedance here with the capacitance give me the decay time constant of my system. And that's how we're going to calculate the decay time constant of our system. It's just the input resistance times the input capacitance. Okay? And do you remember in the derivator and the integrator lab that my integrator works for a specific range of frequencies? It does not work for all frequencies. And the same thing is going to happen here. Our integrator circuit will not work for all ranges of frequencies. Okay? So usually we can control that by change the decay time constant of our circuit. Okay? So the decay time constant of our circuit must be much greater than the period of the signal you want to observe. So let's say you have, a single lightning strike, okay? We have something that we define as flash, a lightning flash. So the lightning flash is the combination of multiple strokes that happen like at the same location at the same time. Usually one flash lasts for like half of a second or sometimes 1 second. So let's say 1 second. Okay? And one pulse, sometimes we can call stroke, one stroke lasts for, let's say, 100 microseconds. It's a super fast pulse. Okay? So if I want to design an electric field measurement system to measure electric field from a flash, the decay time constant for my system must be about, let's say, 10 seconds or I don't know, 1 minute probably. So that decay time constant is much greater than the total duration of my flash. So if I'm interested in measuring the electric field change for a single stroke, probably a decay time constant of like 1 millisecond is okay. So 1 millisecond is 10 times greater than 100 microseconds. Okay? So we can convert this to frequency and get like the same feeling, but looking to the decay time constant is the same thing. Okay? Questions? So I gave you a capacitor. So some of you have the red capacitor and some of you have the yellow one. So you're gonna pick that capacitor, measure the capacitance, pick a decay time constant, and find the resistor you need. Okay?